Kim, it started. All right. So this is, I think, lecture 27 to 28 of probability. The reason the class is a little bit lower today is because what we're going to do will actually be useful for those of you who haven't done problem number 6. So if you haven't done problem number 6, you need to leave when I say it's time to leave. All right, so this is actually related to a paper I published a couple of years ago with two of your TAs, Kayla Miller and Cameron Miller, and some students from Probability 341 a few years ago. All right, so just some general perspective as to what this lecture is about, and then we will go into the details. So the first version of this lecture was given when I was speaking at the 110th annual meeting of the Massachusetts Math Teachers Association of Massachusetts. I think somebody really liked dodgeball. And we were talking about what are the issues of mathematicians, what are the issues of math classes in the future. And so here's a couple of things that we were talking about, that the world is rapidly changing. So what I was taught when I was growing up is very different than what you were being taught, is going to be very different than what Cam and Kayla will be taught. I know Cameron knew how to type his name on a computer before he could actually write it with a pencil or pen. So the real question is going to be, as a professor, what material do we think is important for you guys to learn? What skills should we be emphasizing? Which is why you probably noticed throughout the semester I'm really emphasizing techniques rather than facts. You can pick up the facts. One of the biggest skills to learn is how to think or attack about a new problem, how to see connections. Now, you want to try to do this in a fun way, and so Cam, Kayla, and I thought it would be fun to do it with M&Ms. Because they're the TAs, they get more M&Ms than you. Rank hath its privilege. Okay, so the goals of the talks. I want you to ask questions. Always in life, always in class. This talk actually grew out of a question Cameron asked me when he was 4 years old, and it led to a paper. If you keep looking at things, if you keep trying to find a fresh perspective, this is a great way to make progress. I'm going to use games to get to mathematics. I forgot to update from last year. Cameron is now 9 and Kayla is now 7. I have changed some slides, but I forgot about this one. All right. So who here has played the M&M game before? Great game. All right. We're going to change that. So I want everybody to find a partner. So hopefully groups of 2. All right. Everybody has a group of 2? All right. Everybody has a partner. Excellent. All right. So when Cam was 4 years old, he asked me the following question. Do you want to say the question? Say it loudly.
If you're born on the same day, do you die on the same day?
So how do you explain randomness to a 4-year-old and his 2-year-old sister who has an obsession with everything being the same color? So one possibility is my wife is an identical twin. Well, okay, if I try to use that as a way to explain people being born on the same day don't necessarily die on the same day, there could be family issues. So we need to find a socially acceptable way to explain randomness to little kids that will allow me to see them every day, not just 20 years later. So we came up with the M&M game. Kayla does remember all these years later that she had 4 blues. And what other game do you remember?
I had red, orange, red, orange.
And so the way it works is everyone starts off with K M&Ms. So we did it with 5 M&Ms. You'll do it with 2 M&Ms because the more M&Ms you eat, the less M&Ms we have to eat, and so it also makes the game take a little longer. And then you all toss a fair coin at the same time. If it comes up heads, you eat an M&M, and if it comes up tail, you don't. And so basically think of the M&Ms as your life pellet. So Cam and Kayla will now start playing a game. And you can play your game too. All right.
What is it?
What did you get? And what did you get, Cam?
Oh, please don't say it's going to be the same game as when I was
Yes.
young.
Kayla still talks about the game. She got 5 straight heads. And so if you want, play with your partner. And I will estimate about how many games will end in a tie for the class. All right.
Yes, you are.
All right. So the class will play. Cam is a heads. It's a head.
Wait,
All right.
you should have 1 M&M.
No, I'm watching him. It's a head. It's a tail. Cam, you should have eaten that M&M by now. Kayla gets a head.
I win.
All right.
No, I win.
All right. Has everybody finished their games? Don't take more. No, don't take more. Has everyone finished their games? Oh, we got a winner? Do you think winning is living longer or eating your M&Ms first? Still alive.
I'm still alive.
Dying first seems like
Yes. Yes. Kayla's still alive. Kayla is still alive. Oh, wow, wow. His is more impressive because he only has 2.
Oh, wow.
All right, wow. His head's. All right, so you're now dead? Finally. I've been waiting for Nathan to die for a long. No.
I'm still alive.
Kayla's still alive. It's still tails. Okay, quickly die, Kayla. All right, there we go. Good. All right, stop. Cameron, stop. Okay, sit down and be calm now, okay? So, why don't you guys now move to the front row, okay? And so that you can see the slides. All right, so I'm going to guess that about 2 games ended in a tie where people died at the same time. All right, so 1 person from each team, raise your hand if your game ended at the same time. Okay, just 1. This is the problem with small numbers. The actual expectation was about 1.67. So I had to risk it, I rounded up. All right, so what are the natural questions to ask in this game? Yes?
How many games should end in a tie?
How many games should end in a tie? What's the probability a game ends in a tie? Yes? You gotta speak loudly. You forgot it? Yes?
What is the average of the people, how many of when you eat your second M&M?
Oh, what's the average of when you eat your second M&M? You guys, they're putting you to shame. Yes?
How long will the average game last?
How long will the average game last? What else? Yes?
Probability of winning.
What's the probability of winning? What else could we ask?
When you confer of winning, eating all your
It does depend on the definition of winning. Yes, Kayla?
How many times will it take you to eat all your M&Ms?
That's similar to what somebody else said. How many turns will it take? There's other twists. How could you modify the game?
The other way around. Like tails you eat it, heads you don't.
But it's essentially the same game. It's essentially the same game. I wanted to.
Change the fair coin.
You could change it so the coin is no longer fair. You could have 5 M. Oh, wouldn't life be great if you got 5 M&Ms? If people want to take more M&Ms, if they're at least 15 years old, they can come up during the lecture. If you're under 15, you can get them after the lecture if you're still good. So one of the things we could do is we could have 5 M&Ms. What else could we do?
Have 6 M&Ms?
6 M&Ms. What else? Fundamentally different than adding the number of M&Ms. Yes?
You could change it so you roll a dice and if you roll a 6, you get 2.
Good. So what you could do is you could change how many M&Ms you get to eat at once. No one has ever said that. Good comment. Yes?
You could make a new coin that has just tails.
You could make it, that game would be boring. So yes.
You can make a coin or a die so that if you roll a number, that's how many M&Ms.
That's what he just said.
But if you can't eat all those, you have to wait.
Oh, she has a nice twist. If you have 4 M&Ms left and you roll a 6, you don't get to eat 4 M&Ms.
You get to eat 0.
You'd eat 0. So this is like a lot of board games where if you don't get the exact roll you need. So that's a nice twist to what you had. Yes.
You could have a way to add M&Ms.
You could have a way to add M&Ms still. Last one, Cam.
You could do a dice, and if you roll, say, a 4, and you have a coin and you have a tails, you don't eat for 4 turns.
Oh,
But
okay.
If you have a head, you eat for another.
Okay, so you can do twists. Yes. No, okay. We got to move on. All right, what, Kayla?
If you use a die and you roll, for example, a 6,
Yes?
you subtract 2, so then you only eat less.
Okay.
So if I rolled a 6, I'd eat 4.
Okay. So there's one major thing that nobody mentioned. Maybe Daddy's allowed to play. Right now you're just doing 2 plays. What if you had 3 plays? What if you had 4? We've played that, but now we're doing things with just 2. So here's a bunch of things. So it's important to ask questions. Now, a natural question which was asked is, what's the probability the game ends in a tie? How long does the game? Let's gather some data. All right. So here's the probability of a tie for 2 players. So Cam and Kayla, I want you to sit in the front row now. Okay? Just because I think it would be good for you to be able to see the slides. Okay? You can take the comfy chairs. You can roll them. Okay? So here's the plot. So the probability of a tie. Oh, I had misremembered it. It was 33% with 1 M&M. With 2 M&Ms, it's about 20%. We had 6 groups. So actually 1 is pretty good. I misremembered. So there's a plot of the probability of a tie up to 20. Does anybody have a guess as to what the probability of a tie with 110 would be? Yes? 5%. Okay, we have a guess of 5%. Given that we're already at 5% there, you're thinking that if we go all the way out, it's not going to really drop significantly, okay? It looks pretty flat. How many people really can see what a plot like this looks like? Is this a curve you really understand? No, it can't be normal. What should you do for something like this? Yes?
Log.
Yeah, we're going to take the log. So here is going out to 110. 5% is not horrible, but it's a little bit high. I was giving it the 110th anniversary, so the natural question is, where will we be in 110 years? This is hard to see, so what we're going to do is we're going to take logarithms. Okay? Everybody here, at least above the age of 10, has seen logarithms. You'll see them later tonight, maybe. Okay? What does that look like? Actually, I'll ask Cameron and Kayla. This is your chance to beat the college kids, and if you get this right, you can get an M&M. Okay? Yes. Looks like a right triangle. What does it look like to you, Kayla? What kind of shape does the blue thing look like?
A triangle. It looks like it's making a triangle.
Okay, what kind of shape is just the blue? It looks like a line. Okay, so you can each get an M&M. Okay? No, you can get one M&M. Yeah, it has to be yellow. No, it has to be a yellow M&M. That was not a blue M&M level question. All right?
But the line is sort of blue.
The line is sort. Oh, that is true. All right, all right. You can each get a blue M&M. Today's a casual class. You can each get a blue M&M for that. Does this look like a perfect line?
No.
Why not? Where's it?
Closer.
Where's it bad?
It's like around -2.
Where's -2?
I don't know.
-2. This is -2 over here. So is it slanted in through here?
It's slanted.
A little lower, like down here?
Yeah, basically.
All right. How about class? Where does the class think it's?
It's slanted.
Yes.
If that means you don't have a lot of M&Ms.
Yeah. When we don't have a lot of M&Ms, it looks like the limiting behavior hasn't set in yet, right? If you want, you can have. If you want, you can come up and get a blue M&M for that.
But
Okay.
It's slanted around.
All right. So,
It's slanted like at the beginning.
but in the end, is it looking pretty good?
Can I get a green?
You can get a green M&M. Absolutely. Kayla, go bring him a green. No. Oh, he's coming up. So, all right. All right. So so again, it's very similar to Stirling's formula. In the beginning, we don't have that much data. The limiting behavior hasn't really set in yet. But as we get more data, it should look better. Let's find the best fit line. Do we know how to do this? Yeah, we just did this less than a week ago. Your method of least squares. And if you look at the red line, it does a pretty good job, but it's not perfect. And you can see it's kind of slanting off a little bit. What's one of the issues with the method of least squares?
Things that are far away, far outliers are weighted.
Yeah, far outliers are weighted heavily. So those few in the beginning are really pushing the line. What could we do to get a better fit? I'm sorry? Yeah, so, throw away the initial data point. So when we try to do the best fit line, this is what we get. And so we get the probability of getting k M&Ms is about 0.2412 divided by k to the 0.5456. So when k equals 222, the probability of a tie is about 0.01274, but our answer is 0.0137. Is that good or bad? Would you consider close? Is that pretty close? In terms of the actual size of the numbers, it's not that bad, but in terms of percent error, it's around a 10% error. So percentage-wise, it's bad. In terms of magnitude, it's not bad. We're not talking about a 10% probability. We're not talking about a 1 over 10,000th probability. We have a ballpark answer, but we do not have a very accurate answer. So let's see what happens if we use smaller values. If you now look at just going from, I think, 50 to 110, it's almost straight down the middle. The limiting behavior has really set in, and now, oh, great. So this is the problem, unfortunately, on this board, is that it doesn't go all the way down. It's not showing us. I can't do this and do anything like that, sadly. It's not going to work. So if you actually use the new formula, we get 0.01344 versus 0.01347. So We have a 4 here, we have a 7 here. Extremely good fit from just looking at roughly 60 data points and throwing away the beginning. This is a really important concept to think about. Small bits of data, certain segments of data can be misleading. You need to figure out what to do about them. Sometimes you can remove them for good reasons. Okay, so what I want to do is I want to go from shooting hoops to the geometric series formula. So I want to just start reviewing a bunch of things. I'm going to ask you to leave at this point. So you are excused. I'm sorry. Yes. Yeah, they don't pay college professors that. Now, again, I am happy to let you keep this if you're going to go off into industry and remember me when you become rich and famous. Yeah. All right, have you not done 6 yet? Okay, so. All right.
Thank you.
Yep. All right, so who are these two people? Magic and Bird, right? All right, and why do I use Magic and Bird?
Because Magic is going to beat Bird.
What is so wonderful is, did you know that you could actually give personalized exams at Williams? It's wonderful. So I think we've done this before, so I'm going to go through this very quickly. Bird and Magic are playing a game. I don't know if you have seen this before, so I'm going to do this somewhat fast. Happy to chat about it later. The first one to get a basket wins. Bird always gets a basket with probability P. Magic always gets a basket with probability Q. They never get tired. They never start shooting at a different percentage. And they are willing to keep playing until someone gets a basket. So the game keeps going until someone wins. What's the probability that Bird, who shoots first, gets the first basket? We call that X because we like to call things X when we don't know what they are. All right. So we can break it up into cases. Bird can win on his first shot, probability P. On his second shot, he misses, Magic misses, then he gets. Third shot, miss, hit. And you see in general that for Bird to win on his nth shot, he and Magic miss n minus 1 times, and then Bird hits it. So if we call R 1 minus P times 1 minus Q, then the probability that Bird wins is this nice geometric series formula. Have you seen how to evaluate the geometric series formula? Excellent. So if you knew that, you could then evaluate this and get 1 over 1 minus R. If you haven't seen the geometric series formula, you're stuck. There is another way to attack this without using the geometric series formula. What's the way? Yes?
Recursively.
Recursively. So what's the word I like to use to describe it? I can't remember it right now.
Memoryless process.
Thank you. I couldn't remember it. Thank you. It's a memoryless process. So what's the probability Bird wins? Bird gets a basket on his first chance, or Bird and Magic miss. And now, since they've both missed, it's like we're playing the game from the beginning. So if X is the probability, I'm going to see if Cameron can get this. X is the probability Bird wins. Bird gets it on his first chance, game's over, Bird wins. Assume Bird misses, crap! Then Magic, who sucks, misses. Why? Not even close. That's why he didn't even get to be in the movie Space Jam. Now Bird has the ball. What is the chance Bird wins from this point onward, Cam? This is your chance. This is worth an M&M.
1.
Not 1.
50?
Not 50. This was your chance. It's on the board. X is the probability Bird wins. If they both miss, what's the chance? It's X. So what should I multiply 1 minus P, 1 minus Q by? X. And now we just solve for X. And so when we do it, we get X equals P over 1 minus R. Nope. You didn't get it in time. Sorry. Too slow. Nope, too slow. You said 50. And so we can use this to actually get a proof of the geometric series formula. The 1 over 1 minus R is down here. So you can prove the geometric series formula by considering it as a basketball problem. All right. So this is the power of perspectives. We can circumvent a lot of painful algebra by looking at things more fundamentally. All right. So now let's use this to attack the M&M game. All right. So I'm going to come up with one solution. I am going to overpower this with algebra. Okay? Now I know, Cam, you've seen binomial coefficients, right? Where do you see binomial coefficients? Not the Fibonacci spiral. You actually had them on a homework problem recently.
Oh,
Pascal's triangle. You got to be faster on these. All right? So somebody tell me what n choose k means. This is to review all of the semester. What's n choose k? I'll put you on the spot.
So you have n things, you choose k, and then the probability of like the number of combinations you have.
It's the number of combinations. You need to say another word. or phrase. It's not just choosing k from n. Order matters, right? It's not just it's choosing k things from n where order matters. Yes, is that right? No, it's where order doesn't matter. Okay, I don't care which k I care which k I choose, but I don't care in which order I choose them. So we have our binomial coefficients. Here is a way to calculate the probability of a tie. We're going to do the same thing we did for the bird problem. We're going to see what's the probability the game ends in a tie on n tosses. And then what we'll do is we'll sum over all n. So n has to be at least k if each kid starts with k coins, or k M&Ms. And now what does it mean to have the game end on n? On the nth turn, each one of them has to get ahead. So that's where this 1/2 and this 1/2 comes from. In the first n-1 tosses, each one has to get exactly k-1 heads. So we choose, of the n-1 first tosses, k-1 from bird to be heads, k-1 from magic to be heads. Fortunately, everything is 1/2 because it's a fair coin. This is the sum. So now all we have to do is evaluate this infinite sum involving powers of 1/2 and products of binomial coefficients. Anybody looking forward to this? No. There better be a better way. What way do you think we might be able to use to solve this? What idea might be useful? Memoryless process, right? There was probably a reason we just did memoryless processes, right? So there is a solution that's, depending on your point of view, nice. It is 4 to the negative k times a hypergeometric function evaluated at a special point. This is a little bit beyond what I want to go to in this class, but it's just nice to see where the mathematics goes. And eventually I hope to teach a class in special functions, kind of like WrestleMania with Professor Stark in physics, where we'll be doing the mathematicians and the physicists' view of functions like this. All right, so where did the formula come from? There's really 4 things that can happen. So we're going to do it from Cam and Kayla. So here's the 4 possibilities, and they all happen a quarter of the time. Both eat an M&M. Cam eats, but Kayla doesn't. Kayla eats, but Cam doesn't, and neither eat. Okay? And so that's where we get a formula like this. That's right. Yeah, your M&M will come later.
His M&M.
His M&M. Can anybody see another way of doing this? So we've got 4 possibilities. Yes?
It's sort of like the 2 are sort of the same. Like, you can do it the other way around.
Are you talking about when you eat and when Cameron eats?
Yeah,
but
also both eat or neither eat.
well, but it,
You can just switch those and it won't make a difference.
well, but it matters which one of you eats the M&M.
Yes, that does.
What's another way of looking at this? Right now I'm looking at it as there's 4 outcomes.
Heads and tails?
Well, the heads and tails, but not quite. How can I look at it so there's a different number of outcomes?
We both go out.
I'm sorry?
We start with the same number.
So you start with the same number, but I want to somehow use a memoryless process. How can I use the idea of memoryless process to simplify the analysis?
Well, if both eat and neither eat, then both eat is like starting the game at like, I don't know, at -1.
Okay, so right.
So then you only have 3 cases. You have like, you have the case where they both eat.
Yep.
And the case where one and then the other doesn't.
So we can eliminate the case when neither eats. It's like magic and bird both missing. So we can drop this case from our analysis, and then what would the probabilities of everything be? A third. And that's how we can use the memoryless process. So if we do that, we now get, it's now just 1/3. Now it's a finite game. Because on every turn, at least one kid eats an M&M. Right? And now we have red and yellow trying to come up.
Matthew's M&M.
Matthew's M&M is, which one is he?
Yellow.
He's yellow.
Wait, really?
I did not know, I did not know my nephew is a yellow M&M.
We have some.
You find so much out about families in situations like this. So I'm not going to go through the details as to why this formula is true. I urge you to go through and see why this is true. The slides, I'll make them available, as well as the paper. But the key thing is, it's got to be a finite game. Why? On every turn, at least one M&M is eaten. And so since we start off with 2k M&Ms, we know that worst case scenario, in something like 2k minus 1 terms, it's going to have to go down. Okay? All right. Here's another way of looking at it. I'm going to let Cam have C M&Ms and Kayla have K M&Ms. Why do you think I'm using the letters C and K? Yeah, so why would it be good to use those as the variable names?
So it's like our initials.
So it's your initials, abbreviations. I can quickly look down and see who am I talking about. So we have three things that can happen. I can go from CK to C minus 1, K minus 1, and similarly for the other two. So I can represent this as a tree. I eventually actually got this to be made better using TickX, or no, TickZ from one of my students. I haven't bothered to fix the image. This was done using Microsoft Paint because I was very lazy. But it shows what's going on. So we start here at, say, 4 M&Ms for each one. The tree was long enough that I didn't want to go up to 5. And we want to calculate what's the probability we end up at 0, 0. I'm going to solve this game with a flow. At each point, I have 3 opportunities now. Both eat, Cam eats, Kayla doesn't, Kayla eats, Cam doesn't. I claim that I really don't have to calculate the probability I get here. There's a simpler thing to look for. Which one should I go for? I don't have to look to go to 0, 0. Where should I look to go to? Yes, Kayla?
4, 4.
Which one?
4.
No, I start at 4, 4. I want to calculate the probability I end up getting to 0, 0, but there's an easier place to look at than 0, 0. Yes? Any thoughts? I don't have to go all the way down to 0, 0. Where do I have to just go down to? 1, 1. Excellent. Because the only way I can get to 0, 0 is from 1, 1. Anything else has no arrow getting there. So I only have to calculate what's the probability I get to 1, 1. Now the problem is I could get to 1, 1 coming from 2, 1 or from 1, 2. Or from 2, 2. There's lots of different ways. Okay? Each one of these arrows has probability 1/3. So here is a way to calculate the answer to this problem. I start off at 4, 4, and I flow down, and now I have a 1/3 probability at each one of these. I now flow from these again, and I put a 1/3 probability from this one into these, a 1/3 there, and then a 1/3 down there. And you can keep flowing, keep flowing, keep flowing, keep flowing, keep flowing, flowing, and eventually we get 245 out of 729. And that will be the probability of the answer, about 11%. Okay? This is a nice way to solve the problem. It's not too bad. Now, if instead of giving each kid 4 M&Ms, I said, well, Mom's not here. What Mom doesn't know won't hurt her. Please don't watch this video. Let's give each kid 100 M&Ms. You would not want to do this with 100 M&Ms. Okay, well, I know some people who might want to do this with 100. Yeah, I said, Kelly can go, oh yeah, we're game. But you wouldn't want to do this analysis with 100. I did 100 Hershey Kisses at, yeah. M&Ms is nothing. All right.
Yeah, M&M's is nothing compared to Reese's.
All right, so we're going to switch to another topic to find a better way to get to the answer. Fibonacci. 0, 1, 1, 2, 3, 5, 8, 13, 21. So
34, 55, 89, 144,
233. Where are the students? I mean, come on. This is embarrassing.
No, not really. 377.
377. Kayla's still going, guys. Come on. Oh, wait, 510. But is 510 right or is 510 wrong? Wrong. What should it be?
610.
610. Kim, don't hit that. Is it still focused? You were close. You were only off by 100. Okay.
Well,
so
I'm gonna go now.
don't take this the wrong way, but all right, you can each get an M&M. Stick.
No, I did it.
Kim also got some. Stick to tennis. Stick to tennis. Okay. So we have proved this formula for the Fibonacci's. No. Okay. You've had a lot. I can watch the video later and figure out exactly how many M&Ms you've had. That's one nice thing about recording it. Yeah, I can see a ton. 8. That sounds about right. We haven't talked too much about generating functions, right? Correct? We haven't done generating functions yet.
Nope, not with me.
A little bit. Did we prove Benet's formula with generating functions in this? Okay. In the other class, I know. And so there is a way to prove this. We will prove this with generating functions later in the semester. Here is a way to attack the game. We can set up a recurrence. The Fibonacci satisfy recurrence. Fn plus 1, Fn plus 2 is Fn plus 1 plus Fn. What we can do is, let's let xck be the probability we have a tie given that Cam has C M&Ms and Kayla has K M&Ms. What's different about this recurrence from the Fibonacci recurrence? What's the biggest difference? I haven't given you the recurrence yet, but what do you think is going to be really different? Yes?
There's 3 terms?
So one thing is it might have more terms, but there's something more pronounced than just having more terms. So we had a relation for the Fibonacci numbers fn's, and now we're having a relationship for the xck's. What's the biggest difference? Yes, we have 2 indices. So trying to solve a 2-index recurrence is going to be harder than solving a 1-index recurrence. But if we only need small values, we can just do it by brute force. Some values are easy. If Cam has some number of M&Ms and Kayla has none, Kayla wins. If Cam has...
Didn't I lose?
No, how are we doing it?
She loses because,
All right, you lose. Okay.
because I always win.
All right, we'll do it this way. There's no chance of a tie if Cam has M&Ms and Kayla doesn't. There's no chance of a tie if Kayla has M&Ms and Cam doesn't. If they both have no M&Ms, it's a tie. And then we get this nice recurrence relation. XCK is a third XC minus 1, K minus 1, plus a third XC minus 1K, plus a third XC, K minus 1. Okay? And so this is a lot cleaner than using the flow. We can quickly go down. And so now, what if we didn't see the simple recurrence? What allowed us to make it only depend on 3 things? What was the key insight? I keep forgetting. If neither one got ahead, it's like the toss didn't happen, it was memoryless. Right? What if we didn't see that? What would we have to do if we didn't see that?
Think it didn't happen?
Well, let's say we were not smart and we did not see that we could ignore the case when they both had tails. What would we have to do?
There'd be a lot more.
It would, what Kim?
There'd be a lot more possibilities.
Right, how many more possibilities?
1.
1. So this is the more natural recurrence. I know you got it too. No, you're not getting any more M&Ms right now. Now you got to get 2 questions right to get an M&M. It's getting more challenging. We're in double. Same. All right, you've got 1. Does anybody see a connection between this recurrence and the one above? Because we've just added this term, which term? This term over here, and now the 1/3 become 1/4. Yeah, if we subtract, we'll get a 3/4 multiplied by 4/3, and so we end up getting the same recurrence. So if you didn't see that it was memoryless, you would actually get to the same place, and then the hope is you could go, oh yes, it's memoryless. I see that now. So again, the purpose of today's talk is to really think about how to attack mathematics you haven't seen. If you see the answer, it is a lot easier to solve the problem. Okay, if you don't see the answer, you have to do a little bit more work. Sometimes you can then go back and interpret what you've done. And so if we had seen it with the 1/4, we could then go back and interpret this now as a memoryless process. Okay, so we want to solve the recurrence. So we know x00, 0, the probability of a tie when they both start off with no M&Ms is 1. And now if we want to calculate x11, we just go through, we plug in all the values we know, and we know it's a third. What should we try to calculate next? Which one? Yes?
2, 2.
Okay, but if we do 2, 2, what will we need to know to get 2, 2? We'll need 2, 0, which we know. What's the probability that there's a tie if Kim has 2 M&Ms and Kayla has none? What's the probability? 0. Good.
Yeah.
What else do we need? What else do we need? No. We want to calculate x22. We need x20 and x02. What else do we need? Nope. I'll open this up to the students. This is your chance to take down the kids. 1, 2, and 2, 1. Right? So once we calculate 2, 1, right? Once you calculate 2, 1, why can we calculate 2, 1? Because we can get 2, 1 because it's related to 1, 0, 1, 1, and 2, 0. Okay? So once we know 2, 1, we know 1, 2, and now we can get 2, 2. You have to go through them in the right order. If you tried to do 2, 2 first, you would see you would need these 2, and then you would have to calculate those. Is it that hard to get 2, 1? No. What would we need to calculate next? What should we go for next? I'm sorry? 3, 0. We know 3, 0. 3, 1. We can't go straight to 3, 3. We have to go to 3, 1 and 1, 3. We're trying to get to 3, 3. We have to do 3, 1 and 1, 3. What do we do next?
Then 3, 3? 4, 1?
Nope. We've got...
2, 1.
We just did 2, 1, 2, 3, and 3, 2. Right? So let's try to find an easier problem and build some intuition. All right? So we're walking from 0, 0 to k, k with allowable steps 1, 0, 0, 1, and 1, 1. We want to hit k, k before we hit the top or the right sides. How many of you have seen the Catalan numbers? I don't think I've shown you the Catalan numbers yet. This is one of the only times I can say New York City beats Boston. What part of New York City is really good to drive around?
Central Park?
You really shouldn't be driving through Central Park unless it's one of the Die Hard movies and they're about to destroy a school, and then you got to do things like that.
Brooklyn?
Which grid? Yes.
The grid in
In Manhattan. This is one of the only, not Brooklyn, Manhattan. It's one of the only things I will say nice about New York City. You know, the grid is very nice. You know, Boston, you have Beacon and Comm Ave, you know, flipping as to which one is on top of each other. It's a nightmare driving around in Boston. Manhattan is a nice grid. The Catalan numbers is counting how many paths do you have from the bottom left to the upper right where you never cross the main diagonal. You can hit the main diagonal, but you can't go above it. It's a beautiful problem. The answer, I think, is 1 over n plus 1 times 2n choose n. There's a lot of nice combinatorics. There's a really nice recurrence. There's a lot of great ways of looking at it. I'm not going to go into it now, but what we're really doing is we're doing a generalization of this. We now have 3 ways to move. In the Catalan numbers, you can only move right and up. And in our way,
Left.
can't.
What if you start in the middle?
Not allowed to. Nice to be the professor. You can put in constraints. And for the Catalan numbers, this is where the 2n choose n comes from. How many ways are there to move r steps to the right and, k steps to the right? What am I doing? N steps to the right and n steps up? That's 2n choose n. I have to choose the order in which to do them. But then some of them will not be allowable because they'll cross the main diagonal. Okay? So you can attack the problem this way. Yes?
Can you go like up and then down and then up?
Nope. You can only move right and up. So these are all,
Oh, so you said 2n choose n.
it's times 1 over n plus 1.
Oh yeah, but 2n choose n, right?
Yes.
Number of sequences.
Exactly.
Of course.
And that's why you can see that the answer is reasonable, and it should be less than that. That should be an upper bound. You know, the answer has to be less than 2n choose n because that's all allowable paths.
Yeah.
And so then one of the ways to do it is you could say the Catalan numbers is how many ways to go from here to here without crossing the diagonal. What you could do is how many ways can I go from here to here or from here to here and have that as my first point where I intersect. Well, if I want to have this as the first point where I intersect, one way of doing that is saying that's all the legal paths from here to here, and I start off by going to the right and then going up.
So you said it was 1 over n plus 1?
Well, I think it's 1 over n plus 1 times 2n choose n.
That term.
It's just coming from solving the analysis
That's
for the number of legal paths. It can't be more than 2n choose n. It's depressed a little bit because not all paths are going to be possible. So in the limit, the fraction of paths that work tends to 0.
correct. You can't choose half of
Right. So one way you can do it is you can do it, let me calculate how many paths are there where this is the first time I hit the main diagonal. Or let's say this is the first time I hit the main diagonal. If this is the first time I hit the main diagonal, I know I have to start off right, I have to go up over here. So that's really just asking Catalan paths over here. And then you can get a recurrence relation involving 2 different perspectives. It's not too bad to solve. I'm going to skip that. So I want to end a little bit with the probabilities of a tie. So this is your chance to come back. You guys can try to beat the college kids.
Okay.
All right? So here's the probabilities. 1/3, 5/27, 11 81st, 245 over 2187, etc., etc., etc. Anybody notice a pattern? It's open to anybody. Anything you notice about any?
Are they all equal to 1/3?
They're not all equal to 1/3. Do you notice anything about either the numerators or the denominators?
Where is it
The denominators are the 3, 27, 81, 21, 87, 19, 6, 8, 3.
multiples of 9? Or 3?
This is embarrassing, guys.
I get one, you don't.
No,
Whenever Cameron...
Are you a
Can I
team?
go?
All right, you're a team.
Cameron
All
got
right.
one?
It's nice to have a family team. All right. Are they all multiples of 3?
Yeah.
Do you think the pattern continues?
Yeah, most likely.
Have we done this in class yet? 16 over 64? Have we done this? What's 16 over 64?
You just cross out the sixes.
Thank you so much for ruining the lecture. So 16 over 64 is 1/4. Normally I don't have a smart aleck, but your personalized finals, it's okay. So 16 over 64 is 1/4. 19 over 95 is 1/5. 49 over 98 is 1/2. Yeah. And then I normally get to 12 over 24, and when people say it's equal to 1/2, I'm very puzzled to go, no, it's 1/4. You know, and I cross out all the other ones. It's a dramatic moment. It changes people's lives. You know, now it's ruined forever. But the point is, just because a pattern holds for a couple of terms doesn't mean it's always going to hold. Right? So do we expect that these will always be multiples of 3, or is this just a luck? Is there anything in the problem that makes you think it might be multiples of 3?
Yeah, because it's like ties 1/3 of
Yeah.
recurrences.
That's right. He beat you. He got his hand up faster. Right? Oh, you're stretching. Okay. So, how many of you have heard of the Online Encyclopedia of Integer Sequences, the OEIS?
Have I?
No, you might have actually. The OEIS is a wonderful site. You put in sequences of integers, and it will tell you any place it knows where it sees them. Now, these aren't integers, so what we can do is we can clear denominators. So what I'm going to do is I'm going to multiply by 3 to the 2k minus 1 to clear denominators. And now I get the pattern 1, 5, 33, 245, 19, 21, etc. I've plugged this into the Online Encyclopedia of Integer Sequences. It's sequence A084771. And it turns out this is just a subset. It gives you a whole slew of information about the sequence. It tells you it's the coefficients of 1 over the square root of 1 minus 10x plus 9x squared. It's also the central coefficient of this. It tells you the number of paths of steps. You can see that, oh, that's one of our interpretations. It gives you links to papers. It gives you so much information. The web exists. If you can find a couple of data points, you can try to see, is anything known about it? If you've ever proven things by induction, if you know what you're trying to prove by induction, it's a lot easier. And so you can use this to really guide your analysis. All right. So quick takeaways. All right. So always ask questions. There are many different ways to solve a problem. Some ways are easier than others. Some way highlight different perspectives than others. How many of you know a proof of the Pythagorean formula? You used to. All right. What proof do you know?
I just know, well, I remember seeing President Garfield.
Yes. President Garfield is, I believe, the only US president, and probably will stay the only US president, who has proven the Pythagorean formula. I will not say whether or not I think his trapezoidal proof is very highly derivative of someone else's proof, but he is given credit for coming up with the proof of the Pythagorean formula. How did he die?
He got shot by Charlie.
When? You're so close. You definitely earn one homework exemption problem for knowledge. And why do I care about Garfield? It was on his way to his 25th reunion. So be very careful on your way to your 25th reunion. Yes?
And he would have lived, too, if they hadn't messed with his... When they didn't try and get the bullet out, he would have lived if they just seen the movie.
Yeah. I did not know that part.
Yeah.
But so, one of the most famous Williams alums, a beautiful building on campus in his name.
I'm living there.
That's called Living Still? Interesting. The tape is rolling, so I'm not going to say anything. But what I want you to know is that it's never clear where you're going to go when you start asking these questions. And so this all began with a simple question from Cam as to, do two people born on the same day, will they die on the same day? And we got to see a lot of really interesting mathematics. We got to see memoryless processes. We got to see generalizations of Catalan numbers, hypergeometric functions. We got to see memoryless processes. We got to see anything else, any other ways of solving it? Maybe. Lots of different approaches. Different approaches are useful for different times, or they highlight different aspects of the problem. My favorite proof of the Pythagorean formula is actually a dimensional analysis, where basically because area is squared, the Pythagorean formula has to be what it is. It's the only formula that's consistent with area being products. Okay.
Where do we find?
I'm sorry?
Where do we find?
Where do we find the Pythagorean theorem? Just a second. You find it when you draw triangles and want to calculate, if I give you, say, A and B, and you want to find C, the way we would use the Pythagorean formula, you would have, A squared plus B squared is C squared. And now at least your class has done squares, so I can draw the squares like this and not do A times A plus B times B equals C times C. All right, so this was a nice way to review a lot of what we've been doing, seeing where it can be applied, and just starting to ask questions. It will then lead to generating functions, which is going to be the next major topic. All right.